Hello and welcome to Graphs Engineering. So in this video, we will study the nonlinear analysis of pipe and its support using ANSYS Workbench. So this is the simplified analysis of pipe and its supports, which will be useful for when you will going to simulate the complex pipes as well as its supports, clamps, simulations. So in this simulation, we will try to use nonlinear analysis, that is the contact nonlinearity, by using ANSYS Workbench. So this slide represents our actual problem statement of our present video. So here we need to perform this static structural analysis of pipe and its support. So if you see, this is what the pipe and this is what the support, and you can see here it is nothing but the clamp connection. Okay, and here it is a stopper which is 5 ohm away from this our C angle, or you can say the C channel. Okay, so these are the loading and boundary conditions. So we need to perform the static structural analysis of pipes and its support for following loading and boundary condition. The first, like the material is structural steel. The displacement at one end of the pipe is 9 mm in axial direction. So we need to apply the displacement. You can say that this displacement you will experience due to the external piping which is attached to this respective pipe. Okay. So here we need to apply 9 mm of displacement in axial direction. The bottom surfaces of the supports, you can see here, this bottom surfaces have the fixed support boundary condition. So you mean to say that we will going to log the all degrees of rotational as well as translation degrees of freedom. Okay. The pipe is free to move in axial direction only. So here basically we need to provide the pipe free movement into the axial direction while remaining directions are in lock condition. The pipe should stop its movements once the stopper will reach the pipe support. So you can see that what here we need to simulate. We need to simulate that once we will apply the displacement of 9 mm, then this stopper should come in contact with this respective C channel, and then it will restrict the movement of pipe axial. Okay, so it should restrict the pipe axial movement once this stopper is reached. Okay, so that can be achieved with the help of, there are two ways. The first way, you can define the joint, axial joint, and at the bottom you can define the lock conditions or stop conditions. We will discuss that. And the second condition, or you can, the second way of simulating this is to apply the nonlinear contact, that is frictional contact. Okay, so what we can do now, we can go to ANSYS and then we will discuss the respective simulation. So before going to ANSYS, let's go to our blog post. There we have defined what is the nonlinear simulation and what are the different kinds of nonlinear analysis. So now if you see, we have opened our blog post, that is www.graphsengineering.com, and if you see here, there are so many FEA related topics are there. You can either search from the search menu, or you can even go to here FEA basic, advanced, like that. Okay, here also I think few FEA quizzes are there, you can go through that. So now our today's topic is like nonlinear analysis. So as most of us know that the nonlinear analysis and their types. So you can go through this, you can uncheck this ad. You can go through this blog post, you will find the very good explanation about, or you can say the summary, what are the different kinds of nonlinearity. As we know that nonlinear means the force versus displacement plot is not in straight line, and the steepness of the structure is no longer constant but varies with respect to loading. So when we say the nonlinear simulation, in that case the steepness of the structure is not constant but it may vary with respect to the loading condition. Okay, and there are like three major types of nonlinear simulations. Like when we talk about nonlinearity, first is your geometric nonlinearity. So that is basically happened due to the sudden change into the geometric configurations. So the changing geometric configuration due to large deformation of a structure cause the nonlinear behavior. For example, you might have aware of the large beam you can see over here, and then you are applying the central load about the simply supported beam, as well as the one of the best example, like the spiral springs are there. If you apply some load to the spiral spring, you will find the, or you can experience the large deformation. So that lies under the geometric nonlinearity category. Okay, you can go through the furthermore the blog post. And the second one is like the material non-linearity. So as name suggests, the material is your non-linear material. So for example, your plastic material, your hyperelastic material, your gasket material. Okay, so there are three, like beyond elastic limit for metals, or you can say the within elastic limit for non-metals, and progressive creep deformations. And also you will find that few of the metals which may have your stress strain curve which is not linear, then you can say that that is the material non-linearity. Okay, so you can go through that. This furthermore, there are, you can see the schematic, like here you have the our true stress strain curve. The here up to this you have the linear material, and then here the upper yield point, lower yield point, then you have the break ultimate limit and the breaking point. Similarly, you will have the another material categories like non-metals, which may have the structure is not linear but it is continuously varying. And then you will further have this elastic plastic material. Up to this it is elastic, then plastic, then you have elastic perfectly plastic material, then you have the non-linear elastic as well as hyperelastic material. Okay, so you can see under here also non-linear material, like your hyperelastic, linear elastic, perfectly plastic, elastic, perfectly plastic, elastic, time dependent, we can use in CRIF, and also strain and temperature dependent elasticity and plasticity. So these are the major nonlinear material behavior. Okay, and then you do have the third category, that is the contact nonlinearity. So here you can see that the contact simulation, the frictional contacts, they are frictional, rough contact, nonlinear contact. Then you do have some gap elements, elastic supports, foundation supports. Okay, then you can see, as name suggests, the contact linearity means like we are defining a nonlinear contact. That is what the present topic of our present video. So we can do one thing, we can go to now our ANSYS, and then we will discuss the further this respective simulation. So you can go through this. You can also go through the what are the major possible FEA pitfalls or FEA issues. Okay, so now let's go to the ANSYS. Okay, so I just open the my pipe support and frictional contact file. So you can simply drag and drop your static structural analysis deck into your project schematic. Okay, you can open or you can import here, right click, and then you can import your respective geometry. Okay, transfer data from new, and you can even open from inside the SpaceClaim. So let's go to the SpaceClaim. So you can open from here. Okay, if you have the respective directory path, or you can create this new geometry here itself. For the creation of this, it is quite simple. You can refer to our SpaceClaim modeling videos. Okay, you will get the complete insight how we can model this 3D structure. Okay, so it is quite simple structure which may consist of a pipe, and you can see this is what the clamp. Okay, and this is supported on this respective C channel, and here it is the stiffener plates through which it is rested on this bottom face, and these are also the stiffener. This is also the 3C channel. So this is the simplified structure, but when you refer to the petrochemical industries, you will have there a number of pipes and number of clamp supports are there, and in that simulation, or you can say that in that cases, you will have the respective pipe which is subjected to your temperature as well as pressure loading conditions, and due to temperature there might be possibility of thermal expansion. So in order to avoid the larger thermal expansion, you can provide the stoppers like this, which is welded to this pipe, and there is some gap between these two. Okay, suppose due to the temperature loading condition, or you can say that due to the external loads, this pipe may move, okay, into this clamp. So you can put this stopper if you want some certain amount of displacement. Okay, so that is what the use of this stoppers. Okay, so once you will create the geometry, you need to share the topology. Okay, for this we have combined this whole structure into the one single component. You can see inside this, and that is why we will going to name that. You can name here if you want to rename. Okay, here rename option is there, and you can rename that, and here under this you can use the share topology, so that all adjacent faces will going to merge with each other. Okay, now let's go to the our model, and let's open the ANSYS mechanical. Okay, so the very first we need to define the material, but as we know that in ANSYS by default material is a structural state, so there is no need to define that. So you can see the material details, and if I can show you how to define, you just need to double click over here, and then here you can define the new material, define the physical and elastic properties from here. Okay, let's go to the mechanical further. Now once your geometry is open, your material is defined, then you need to define the connections, which is really important topic. So by default ANSYS will generate the contacts. So let's check the each and every contacts. So this contact is between the pipe clamp, you can see, and the pipe support. So here, as we know that it will going to move only in axial direction, so instead of defining contact, let's define the joint. So I will suppress this. Then at the bottom also you can see that this contact is between this respective pipe and this stopper. You can either imprint this on this pipe, or you can keep as it is, because it is bonded contact, so there is no need to worry about that. Then the third one is like between this, so as we discuss, we need to define the joint, so we can suppress this. Now the next contact between these respective bolted joint connection over here between the bottom face. Okay, I can show you over here, and this top face. So we can keep as it is, as we are not modeling bolt. So we are idealizing bolted joint by using bonded contact connection. And the next contact is between this topper. You can see this topper and this face. So this is really important contact, because we will going to define this contact with the help of frictional. So let's do one thing. Let's try to do suppressing this, and let's try to simulate the simulation, and then we will check whether it will going to stop or not. Okay. If not, then we can think about how to define the frictional contact and what are the different frictional contacts are there. And let's talk about the meshing. So at present, this is simple structure is there, so you can either define the global sizing, or you can right click insert and you can define the sizing over here. So I will keep just simple 10 mm sizing, okay, and just mesh the overall structure, generate mesh. So always keep in mind, whenever there is a frictional contacts, try to mesh the both contact and target surface with the same mesh size whenever there is a frictional contact. For bonded contact there is no problem, but when we talk about frictional contact, then there you need to think of keeping the same element size. So as we just need to know how to simulate the nonlinear simulation, so that is why we will not going to focus on this. So if you want to make it hex dominant, you can simply method select all, apply, and here you can define the hex dominant, and let's try to mesh with that. So whenever it is possible, it will try to mesh hex dominant. So if you see, the mesh is performed but with the errors. So you can see on the screen like the measure has failed to generate the hex dominant mesh for one or more bodies. So there are few bodies which are not sweepable or mappable for which the hex dominant mesh is not possible. So you can check that. Once you will find the error, right click, show the problematic geometry. So you can see like this. Similarly, you can repeat the for another geometry. So likewise, if you have bigger or complex geometry, you can investigate, and then in order to create the proper hex mesh, you can go step by step, try to make the first sweepable or mappable geometry. So you can go here, show sweepable bodies. Okay, so likewise you can go one by one to create the mesh, and also there are different methods to perform the mesh, like automatic is no automatic is by default, it will create the hex as well as state mesh. Then tetrahedron, hex dominant, sweep, multi-zone is also possible to create the hex mesh. Okay, so you can refer to our meshing tutorial in order to get the more insight of this. So I will just clear this. At present we will only focus on the loading boundary and how to achieve the frictional contact. So I will keep the 10 mm as it is and then try to generate the mesh. So once the mesh is performed, then we will move to the next step, that is to apply the loading and boundary condition. So if you see here, whichever is the geometry which is possible hex, it is created the hex, which is not possible tet, it is created the tet. So here we have the impression of this body on this, so that is why it is not created the hex dominant mesh. So for that you can create the slice or you can use the multi-zone. Okay, now let's talk about the loading and boundary condition. So before going to that, we need to create first the axial movement between this clamp and this pipe. So for that we can use the joint. Okay, right click, hide body, and for the joint you can select all the outer faces and then apply. Okay, now select the outer faces for the pipe and you can apply it over here. So we have applied a joint over here, right? And now let's define the joint type. So in our blog post I also I think covered the types of joint and what is their use. So at present we will use the translation joint. So you can use either translation or you can even use the general joint, and there you can relax the x-axis. So here you can see that x-axis is free. Okay, so that this pipe will move in axial direction along this respective clamp, and while other remaining degrees of freedom are locked conditions. So as discussed, there are two ways to make it lock in order to achieve our loading condition, that is 5 mm of this. So here you can see the stops, and here you can define the x stop, and here you can define the 5 mm. Okay, once you will define this x max and minimum condition, okay, I will make it none, then you can use the here the large deflection on. Okay, then it will fall under your large deflection nonlinear category. Okay, so that is also possible, but most of the times it creates a problem to go with this stops method. So that is why the most useful method is to create the frictional contact if you want to achieve a certain amount of displacement. Okay, now let's apply the loading and boundary condition. So select these two faces, right click, insert, fix support. So we are locking all degrees of freedom, and on this face we are applying the right click, insert, displacement in x direction, that is 9 mm. Okay, you also need to check the direction of the arrow. So if you want to increase the scale, increase like this. Okay, and now you can check the arrow direction. Okay, so at present we have not given any contact between these two bodies. We want to check whether with 9 mm displacement this stopper will going to stop at this respective body or not. Ideally, it will not going to stop because in FEA we need to define the input conditions. So now if you see, our simulation is performed. Now let's extract the deformation as well as right click extract the stresses. Right click evaluate the results. So now if you see the deformation which we applied, that is 9 mm, and we are getting the 9 mm deformation for the whole pipe. It means that there is no stop at this respective stopper. So let's check that with the animation. So if you animate, you will come to know that whether it is restriction. Okay, I do not find any restriction, but this is still moving inside that because we have not given any contact, and ANSYS will not read by default it. So that is why we need to give the contact. So if you give the bonded contact, then you will not going to get this movement or the stopper 5 mm movement. You only need to give the frictional contact for this. So if you want to increase some scale, you will see how it is moving. This is virtual scale which we have given. Now we can see. So the thing is that if there is no restriction for these pipes, it means that there should not be any stresses. So let's check that. Okay, so if you see, the stresses are almost 0. Okay, so it means that you need to define the contact for that. So let's check this contact height all other bodies. Okay, so what we can do now, we can define the frictional contact, make it frictional. So there are two linear contacts. First is bonded and second is no separation. In no separation, some sort of sliding is allowed. Frictionless, rough contact and frictionless contact. Frictionless contact means you can see that there is no coefficient of friction. Okay, and there is rough contact. You can also define that rough contact, and there is a frictional contact. If you have some sort of coefficient of friction, so coefficient of friction based on your material to material connection. So right now steel to steel, you need to Google it that, and I think it is between 1 to 0.05. So accordingly you can define that your frictional contact. And there is a behavior like asymmetric, symmetric and autosymmetric, so you can keep program control. So I will suggest you can keep most of the setting program control, because ANSYS will automatically calculate based on your the contact stiffness, your material properties, your meshing. Okay, and formulation, there are different formulations are there. I will create a separate video for this this setting for this. And the very important point is like here you can define the normal stiffness. Okay, if you want to put some values of normal stiffness, you can define that values factor. Okay, and there is also, you will have some sort of stabilization factor which helps to converge the solutions. Okay, and if you want to give some pinball also, it is possible in frictional contact. And these are the very important interface treatments, like adjust to touch is also important. It will, right now if you see, there is a gap between these two bodies, 5 mm gap is there, and if you are using adjust to touch, it will initially close the gap. And suppose if there is interference, then it will remove that interference and it will simply touch the respective body. Suppose if you are facing issues with the convergence with the contact, then this setting is really very useful. And adds offset and ramp effect will create your offset between these two body, and it will, when we talk about add offset ramp effect, it models the true contact and gap penetrations. okay, between these two bodies, it ramps the interference linearly with all the substeps. And here, in case of no ramping, it will not going to, you can say that it will applies the interference all in a first substep. In previous case, if you have applied some substep, then it will apply in a in substeps. Like if you have 5 substep, then it will apply in first substeps 10%, then 20, 30, like that. But in case of no ramping, it will going to apply in a first load step itself. Okay, and here it is adjust to touch option is there. So likewise, you have different options, and here you can define the offset. Okay, and also there are few further if you want have some sort of smoothing treatment, then you can define by using contact and your target geometry corrections. So there are a number of things like we can create a separate video on this, and then we will discuss the in more depth. At present, you will keep the program control, okay, and you can define the frictional contact, and you can define the your coefficient of friction. Okay, make it unsuppress. And when you will define the frictional contact, it is better for you to define that into the number of substeps. So I will keep on. So there are two ways. Either you can define by substep. So here you can define the number of substep you want, or else you can define the time. And here you can define the minimum time step. And so this is first initial time step, then minimum step and the maximum step. So let's keep it the substep. Let's keep the initial substep, minimum substep, and then maximum substep. Okay, so we will keep the 10 substep. So it will solve into the 1 to 10 substep. So let's right click, clear the solution, and then solve the simulation. So now if you see our simulation is performed, let's display first the all bodies, and let's check the global displacement. Okay, it is also 9 mm, and at this location we do found it is the color is slightly changing. It means that there is a stopper is working. So let's put these stresses. Now the stresses are increased. It means you will find that at this region you have a very high stresses. That is because of it is restricting the movement of the pipe. Okay, earlier we have not received any stresses. Now we are getting a very high stresses. This is just the we have considered the approximate boundary conditions and loading conditions. In actual, this displacement might be due to your thermal expansion or might be due to your external piping. So you can apply the actual load, then you will get the realistic stresses. So at present we are just focusing on how to perform the nonlinear analysis with the help of frictional contact. So let's display that only two bodies, and let's check with the deformation. So now let's see the respect to deformation. So if you can make it a scale, you can see that right now your respective body came into contact and there is a slight deformation of this body. If it is quite rigid, then it will not allow this respective body. But right now it also have some stiffness. So due to this, it is pushing that into inward. So let's check the deformation values over there. Result probe. On this body you have 3 mm of deformation. Here you have 7 mm of deformation. Okay, here also 3.2. So due to this push movement, it is moving 3 mm inside, and it is reducing the by 2 mm approximately. Okay, and that is why we do have very high stresses over here. Almost all the bodies are having very high stresses. Okay, once you will apply the realistic displacement, then you will get the realistic stresses. But there is such cases when you have a complex geometry and you want the pipe movement to be restricted by the stopper, so in that case you can use this respective frictional contact, okay, with the stopper, and also define the analysis setting, like you can define the multiple sub-step. The advantage of that is, I will show you. If you go to the solver output force convergence, go to the solver output, here you will find that it is only solved into the fourth sub-step. If you have even given in first step itself, it got converged. This is the internal force and this is the force of convergence. It should coincide with each other. If not, then there will not be conversion, will not be achieved. Okay. So that's it guys for the present video. At present we are only focusing on how to perform the non-linear simulation. In next simulation we will more focus on the analysis setting for frictional contact. So thank you. Let's see each other into the next video. If you have any comments, please comment into the comment box. We will try to reply.